Hello students, welcome to EPG Pathshala. I am Dr. Devrat Mishra from Department of Physics and Astrophysics, University of Delhi. Today we are going to discuss about the module Optical Properties 5 from paper Electronic, Magnetic and Optical Properties of Materials. So students, let us see what we are going to learn in this module. So we will see the absorption spectra of a semiconductor and its dependency with the wavelength. And then we will learn about the conductivity effect of a semiconductor, photovoltaic application of semiconductor and its dependence on intensity. And we will see and we will learn about the different luminescence property of a semiconductor. Optical properties of semiconductors. Absorption spectrum. Many semiconductors such as silicon, germanium, indium, arsenide and others exhibit typical metallic luster when viewed with ordinary light. When viewed with longer wavelength infrared radiation, however, the crystals are rendered transparent. Figure 1 shows the variation of the linear absorption coefficient with changes in the wavelength of the incident light used for two germanium crystals. Starting with the longer wavelengths and moving towards the shorter wavelengths, move from right to left in figure 1, it is observed that the absorption coefficient decreases, indicating that the crystal becomes more and more transparent to shorter wavelength radiation. This is consistent with the greater energy of the photons of shorter wavelength radiation E is equal to hc by lambda at 2 micrometer. However, the absorption coefficient begins to rise until at approximately 1.7 micrometer it becomes extremely high. The reason for this abrupt increase in absorption becomes evident when the band model of germanium is considered. The energy of the radiation corresponding to a wavelength of 1.7 micrometer is 1.5 into 10 to the power minus 12 or 0.72 eV, which is the width of the energy gap in germanium. Thus, a photon having this energy is capable of exciting an electron occupying a quantum state at the top of the valence band to a quantum state at the bottom of the conduction band. In the process, the energy of the photon is absorbed and the crystal appears to be opaque to radiation of this energy. Still, shorter wavelength radiation can excite electrons from lower energy quantum states to other states in the conduction band. The increased number of free electrons thus produced accounts for the metallic luster of germanium, since these electrons can absorb energy by transition to higher energy quantum state in the conduction band and re-radiate it by transition to unoccupied lower energy states. Actually, these transitions take place through electron-phonon interactions because direct transitions are not allowed. Note that a lower resistivity germanium crystal has a greater absorption at all wavelengths. For this reason, as shown by the two curves in figure 1, lower resistivity of course means that there are more conduction electrons present and or between states in the valence band of the localized state. The energy value of the wavelength at which the absorption maxima occurs. It can be seen from this discussion that absorption measurements can be used to determine the nature of the band model of semiconductor. Although it is possible to determine the energies of donor or acceptor states by this means, it is necessary to perform the experiments at very low temperature in order to minimize thermal excitation of the electrons. Photoconductivity. The increase in the carrier density produced by the irradiation of a semiconductor contributes to the crystal's conductivity. When an electric field is applied to the crystal and radiation of an appropriate wavelength is allowed to fall on it, an increase in its conductivity is observed. This property of photoconductivity is utilized in a large number of device applications, the most obvious being simply to use the crystal as a detector of radiation. Since pronounced photoconductivity occurs when the crystal is irradiated with radiation having an energy greater than the gap width, various kinds of radiation such as visible light, X-rays, electrons or nuclear radiation can be detected in this way. Some of the difficulties arise in describing the process whereby an electron excited to a quantum state in the conduction band by the absorption of a photon can recombine with the hole produced in the valence band. As previously stated, the electron and hole do not recombine directly. This is because the probability for such a transition, measured by the so-called capture cross-section, is very small, which is of the order of 10 to the power minus 21 centimeter square, as compared with the capture cross-section of an imperfection, which is of the order of 10 to the power minus 15 centimeter square. Direct recombination becomes a significant factor only when the concentration of free electrons is very high, which is of the order of 10 to the power minus 19 centimeter cube. Consequently, recombinations usually take place through recombination centers with a rate that depends on the nature of the imperfections, that is, its relative electron and hole affinity. The difference in the mobility of electrons and holes also affect the recombination process. The description of photoconductivity given below is derived from empirical observations rather than from fundamental principles. Such theories are usually called phenomenological theories for this reason. If the absorption of photons produces F electron-hole pairs per unit time, the increase in the density of electrons and holes is given by delta n is equal to F into tau n and delta p is equal to F into tau p respectively. Here tau is the effective lifetime and the subscript denote the type of carrier. The resulting change in conductivity can be determined with the aid of delta sigma is equal to E into delta n into mu n plus E into delta p into mu p, and delta sigma is equal to E into F into tau n into mu n plus tau p into mu p. The relative contribution to the observed conductivity may be different for holes than for electrons. This can be caused by differences in either their relative lifetimes or their mobility or both. Also, it is apparent that in order to measure an increase in conductivity, delta sigma must be of the same order as the conductivity in the absence of radiation. This means that crystals having small values of dark conductivity, for example, certain insulators, generally are better photoconductors. If capital F is the total density of free carriers per unit time produced in the crystal, then the photocurrent IL is given by IL is equal to E into F into tau by T tau, where T tau is the time spent by an electron in transit between two electrodes. This is called transit time and it is determined by the inter-electrode separation L and the average drift velocity of the carriers according to T tau is equal to L by average of V, which is equal to L by mu into epsilon, where mu is the mobility and epsilon is the applied field. Noting that the applied field, which is volts per centimeter, is equal to the applied voltage V divided by the inter-electrode separation, it is often more convenient to express 4 as T tau is equal to L square by mu into V. Note in equation 3 that the larger the effective lifetime of the carriers relative to the transit time, the larger the photocurrent becomes. Physically, the following events take place. Suppose that the lifetime of the electrons is greater than the lifetime of holes. This means that a hole is quickly trapped while the free electron is swept out of the crystal by the applied field. In order to preserve charge neutrality, another electron is emitted by the negative electrode, the process continuing until the free electron recombines with the hole. Thus, for each photon absorbed, there appears to be more than one free electron contributing to conductivity. This apparent gain can be expressed directly by a gain factor, which is equal to G is equal to tau by T tau. It follows from the definition of the gain factor G in the equation 6 that it can be used as an indication of the efficiency of a photoconductor. According to 4, one way to change the gain is to change the inter-electrode separation. Another way to change the gain factor is to change the composition and perfection of the crystal. This is so because the effective lifetime of the charge carriers is inversely proportional to their average velocity v, the number of trapping centers n, and their capture cross section s. When such a crystal is then placed in a transverse magnetic field B, the electrons and holes are deflected through the Hall angle to opposite sides of the crystal. This produces a current which can be measured, and the phenomenon is called the photoelectromagnetic effect, frequently abbreviated to PEM effect. If the PEM current IL is measured simultaneously with the photocurrent IM, it is possible to obtain a relation for the effective carrier lifetime in terms of both effects. That's such that tau is equal to capital D into whole square of IM by epsilon into B by IL whole square, where D is the diffusion constant for the crystal and epsilon is the applied field. This is one example of the way in which different semiconductor properties can be combined to produce new effects. Such combinations are equally useful in the study of particular property and in the design of a new device. Photovoltaic effect. It is possible to grow a single crystal containing both p-type and n-type regions. The boundary between two such regions is called a p-n junction and has some very interesting properties. Consider a crystal composed of two such different regions and a transition zone between them as shown in figure 3. When the light is incident on the crystal, electron-hole pair are produced in the crystal and electrons diffuse into the n region while the holes diffuse into the p region. In the absence of an externally applied field, the light-induced current develops a photovoltage across the crystal, and this phenomenon is called the photovoltaic effect. Such a crystal obviously can be used as a battery whose energy is derived from, say, visible light. In order to see how this so-called photovoltaic cell functions, some of its important properties are described below. Suppose that an external voltage V is applied to the crystal in such a way that P region is biased positive with respect to the N region. Then, in the absence of light, the current is given by I is equal to I0 minus I0 into exponential of EV by KT, where I0 is the so-called dark current. Second term represents a current in the reverse direction. If light is now allowed to fall on the crystal, an additional photocurrent IL is produced and the total current becomes I is equal to IL plus I0 minus I0 into exponential of EV by KT. When no external voltage is applied to such a crystal, I is equal to 0 and the crystal becomes a photovoltaic cell. The voltage developed across the two ends of the crystal then can be determined directly from 10, denoting this photovoltage V. I is equal to 0 is equal to IL plus I0 minus I0 into exponential of EV by KT. Rearranging the terms in 11, we have exponential of EV by KT is equal to I0 plus IL by I0. And taking natural logarithms of both sides in 12, EV by KT is equal to ln of 1 plus IL by I0. This relation can be solved for the photovoltage V is equal to KT by E into ln of 1 plus IL by I0. For very large light intensities, IL by I0 is very greater than 1, so that according to 14, the voltage varies logarithmically with the photocurrent.
This is the reason why photovoltaic cells are so useful in ordinary light meters.
Luminescence. An electron that has been excited to the conduction band can return to a lower lying allowed state provided that such a transition is accompanied by the emission of an appropriate quantum of energy. The number of different transitions possible is determined by the number and kinds of allowed states lying in the forbidden energy bands. Consequently, these phenomena can be rather complicated. The term luminescence is used to describe the phenomena whereby a crystal absorbs energy, usually in the form of radiation, and re-emits it in the form of visible light. If the crystal emits light simultaneously with its excitation, the process is called fluorescence. If it takes 10 to the power minus 7 seconds or longer to emit its light, then the process is called phosphorescence, and the crystal is called a phosphor. Furthermore, there are two distinct processes for luminescence, both of which require that impurity atoms called activators be present in the crystal.
In the first process, the incident quantum of energy is absorbed by an activator atom by a transition of one of its electrons from one quantum state to another. When the excited atom returns to its ground state, it loses energy by emitting a photon of energy h nu is equal to E excited minus E ground, because the allowed transitions are characteristic of the energy levels of the activator atoms. This process is called characteristic luminescence. The second process is more complicated. Consider a divalent metal sulfide in which a number of monovalent cations have been substituted for the metal normally present in the crystal. Other ions, called co-activators, must be added to the crystal in order to preserve charge neutrality. When an electron-hole pair is produced by an absorbed photon, the hole wanders through the crystal until it is trapped at the site of an activator ion. The actual process can be pictured as a diffusion of the extra electron belonging to the activator ion until it combines with the newly created hole. Thus, the activator first acts as a hole trap. When the free electron later recombines with the trapped hole, a photon of light is emitted by the crystal. The color or the frequency of the emitted light depends on the nature of the trapping centers present, which in turn depends on the type of imperfection introduced. For example, two processes have been suggested to explain why copper activated ZNS emits blue and green light. Actually, emission bands having other frequencies are also observed, but they are relatively much weaker. Based on the known ionization energies for copper, it has been shown that the blue light is emitted when copper plus 1 substitutes for Zn plus 2. On the other hand, in order to explain the strong emission of green light, it is necessary to assume that the substitution copper is divalent and that the ionized electron combines with interstitial copper plus 1 ion so that the interstitial copper atoms are neutral.
The above example has been cited merely to illustrate the involved nature of the luminescence process. Without going into further detail, some other ways to produce luminescence in crystals are listed below. When luminescence is produced by either visible light or ultraviolet, infrared or X radiation, it is called photoluminescence. When a phosphor is irradiated with high energy electrons that lose their energy by electron-electron collision in the crystal, the secondary electrons lose their extra energy by recombinations at trapping centers, and the process is called cathodoluminescence. It is also possible to produce luminescence by exciting the electrons electrically. The phosphor is placed in an insulating medium having a very high dielectric constant, and an alternating electric field is applied across the crystal. The very large electric field strength built up inside the phosphor is sufficient to empty an activator quantum state. When a free electron recombines with the hole, thus produced light is emitted. This process is called electroluminescence, and it has been observed that the emitted light is a function of the voltage and frequency of the applied field. Finally, suppose that a phosphor has been excited by any of the above means at very low temperatures.
The decreased thermal energy or velocity of the electrons retard the luminescence process until the temperature of the crystal is raised so that it appears that the luminescence is thermally produced. This is called thermoluminescence and is particularly useful in studying the energy levels of the impurity quantum states because the amount of thermal energy gained by the electrons upon hitting the crystal can be measured quite accurately.
So students, let us summarize what we have learned in this module. Absorption spectra of a semiconductor and its dependency with the wavelength is explained. Photoconductivity effect of a semiconductor and its dependency on various parameters is explained. Photovoltaic application of semiconductor and its dependence on intensity is also described. Different luminescence property of a semiconductor are also explained. Thank you.